Welcome to Ask and Learn.
Here we are given a sports car weighing 2.3 times 10 to the 3 kilograms, and it is traveling at 28 meters per second, and the driver causes it to accelerate at 5 meters per second squared. We are told that the drag resistance on the car due to the wind is given by this equation, 0.3 times the velocity squared, and we would like to determine the power supplied to the engine at this instant. So we'd like to calculate the instantaneous power. We are also told that the engine has a running efficiency of epsilon equals 0.68. Therefore, we will first calculate the power required for this acceleration to occur in this force condition, and that will give us an instantaneous power. But then we will have to convert that to the amount of energy or power derived from the engine, given that it does not have a 100% efficiency. So first, we would like to calculate the force and the velocity. We actually have the velocity already because this is instantaneous, and we have this is just v0, 28 meters per second. We also can calculate the force, since we're given the force of drag is just 0.3 v squared, right? But we're also told the mass, and we're told this acceleration here. So we are accelerating forward 5 meters per second squared, yet we are given a drag force backwards of 0.3 times v squared. So it's traveling at this speed, and we cause the car to accelerate. Drag resistance will be pushing back on the car at the same time that we're trying to accelerate. Then we're going to be able to calculate a total net acceleration, which will give us a total net force by Newton's second law. So remember the net force, which we'll use in the power equation, is just the mass multiplied by the acceleration, the net acceleration, that is. And here we're going to have the mass, 2.3 times 10 to the 3 kilograms. I'm just going to write that as m again, multiplied by a, 5 meters per second. M times 5 meters per second. That's going to be in the forward direction here. But we'll also have a force in the opposite, negative direction. That's going to be a minus 0.3 v squared. V is just 28 meters per second squared. Second squared. Okay, so let's just use a calculator here. And actually, I'll divide by let's see. Well, we don't need the this side of the equation here, right? Because we just like to calculate the total net force. This equals the net force. So let's plug in this mass here. We have 2.3 times 10 to the 3 times 5 minus 0.3 times 28 squared. That's just the numerics. So we have 2.3 times 5 will give us 11.5 times 10 to the 3 minus 0.3 times 28 squared. Oops. 0.3 times 28 times 8 equals 235.2 minus 235.2. And that 11.5 times 10 to the 3, 10 to the 3 is 1,000. So we have 11,500. 11,500 minus 235.2, which is 11,264.8. 11,264.8. That's in newtons. That's going to be the net force that we'll use for the power. Okay. Oops, I need the shape on. Okay, then we'll just use that V0, and we have P equals 11,264.8 times 28 times 28. That's going to give us 315,414.4 watts. My power is in units of watts, joules per second. And now this is the power that is exerted on the system overall. But if we look at the amount of power required by the engine, we're going to have to divide by its efficiency, 0.65. Because if it was a perfectly efficient system, it would be like dividing by 1. But if it's slightly smaller, then we're going to need slightly more power, because some of that power will be reduced to waste by heat, for instance. So we'll be taking this 315,000 power of the engine is just the standard power viewed from outside the system divided by the internal efficiency. So that's going to be 0.65. And that gives us 485,250. 485,200, let's say 53 watts. So this is the amount of power supplied to the engine at this particular instance in time.